your outline, so you're going to need to add that one to it. I forgot about this one. Okay? All right, so this is going to be a chi-square. You guys are already kind of familiar with it. So here's what I'd like to do. Make sure you guys are good with the computer. You can do this one on the computer. Okay? All right. Okay, suppose the standard deviation of weight of candy was 0.75 grams for machine calibration. QC wants to know if calibration results in more consistent weights. Okay. Now we've been giving you mostly summary statistics, so let's actually do ask us to do one that wasn't the same. So here's your data. Okay, raw data here. 19.68, 19.98, 20.55, 25. Okay. All right. So the first question is what? Categorical, quantitative, or rejection? Answer is quantitative. Okay. Second question is what's the test statistic? And you said chi-squared. So I ought to give you the equation of that, right? Okay, so the equation for the chi-squared is n minus 1 times s squared over sigma squared. Okay, that's your new equation for the day. Okay, so it's going to be n minus 1 times s squared over sigma squared, which means you've got to figure out what all that stuff is. N equals s equals and sigma equals. Okay? How do I find my n quickly and easily with the computer? Highlight your data. I've got n equals 11. Oh, and by the way, we're going to need to do 3 and 2, right? Chi-squared. S. How do I find my s? What'd you say? Standard deviation of this. Right? Okay. 0.64. Does it look like the recalibration might have helped? Yeah, it can get worse, right? Okay, sigma is what? 0.75 degrees of freedom. 10 degrees of freedom. Okay? Alright, so I'm going to plug this in here. I'm going to take my 10. I'm going to multiply it by my standard deviation, and I got to square that. Okay? Probably been wondering all this time, why did I care about variance? This is where I'm using the variance. Okay? Sigma is going to be 0.75 squared, right? So we got the variance there as well. Okay? I'm going to divide those two numbers. And that gives me, this is my chi-square statistic. Okay? All right. So now, next step is my null and my alternative hypothesis, right? So h sub 0 and h sub 1. Okay? My null hypothesis is what? Sigma equals 0.75. Okay? Alternative hypothesis. So they want to know if it results in more consistent weights. What does that mean?
Less deviation.
Maybe less standard deviation, right? Okay? So my alternative hypothesis is sigma is less than 0.75. Does that make sense? Okay? All right. Let's see, so that was step number 3. Step number 4 is your alpha, right? What's my alpha? What is it? 0.05 because I didn't tell you. Okay? My p-value. Okay, my p-value is next, right? Okay, if you, so I can do the table, I'm going to have to bracket it, or I can do the computer. If you were going to write a command for the computer, what would you use? What's x squared? Now this one's a lot like the T, because I can do a right-tailed test or I can do a left-tailed test. Okay? Notice there is no two-tailed test. Why do you think there is no two-tailed test? It's not symmetric. It's ugly, right? Okay? So that's why. So this one without the RT, what do you think that one is? That's a left-tailed test. That's the one I want. Okay? What do I put in here for x?
0.729.
That's the what? 7.29.
7.29.
The degrees of freedom? 10. Do I want cumulative? Yes. Usually going to want cumulative on these. The binomial is the exception. Sometimes I don't on that one. Okay, so the p-value works out to be 0.30. Now I'm going to show you how to do this a bunch of different ways. Let's just continue on with this. What's the next step? We're going to compare the p-value with my alpha. When I compare those, reject or do not reject? What? Vote? Reject. Who says reject? Nobody? Who says do not reject? Okay, majority words. Do not reject. Okay? That means what? Has the recalibration resulted in more consistent weights?
There is not.
There's not enough evidence that recalibration okay. Now it looks like it went down. It might have gone down. We don't have enough evidence because we only tested this on 11 candy bars, right? So maybe it helped, but we don't have enough evidence. Okay? Maybe if we sampled more. Okay? But that would mean we probably couldn't sell those. Okay? We put a blue finger on. Alright. Does that make sense? Okay, so let's talk about p-values. How do we do it other ways? So there's another command here. This one has no periods. Chi-dist. Chi-dist with no periods. Okay? Now, what do you think we put in for x? That's going to be my 7.29. What is my degrees of freedom? Still 10. What do you notice about that? Not only is it more than double, but it also looks like kind of like a complement, right? So it's telling you what's to the right. I want what's to the left. So if I do a 1 minus, it'll give me what's to the left. Okay? Now, I probably should have showed you the picture because remember, when we're looking here at my chi-square distribution, it says what's to the right. So the Excel works just like this table does. Okay? That's why I need to do the 1 minus. So if I want the area to the left, I gotta do 1 minus. Okay? All right, so now as we're looking at this, okay, what did I say? I can't remember. My degrees of freedom was 10, wasn't it? My alpha was 0.05, and my chi-square was 7.29, as I remember. Right? Okay, so if we're doing this, we want to find the p-value. We know that with the chart, all we can do is bracket it. Okay? So if I'm at 10 degrees of freedom, 10 degrees right here, where does 7.29 fit on this line 10 here? Fits in between those two numbers, right? 7's in between those two numbers. I go up, I'm in between 0.10 and 0.90. Not kind of a big gap there, right? Okay, and then we know the answer was 0.30, so that is in between those. Okay, so that's the best we can do with the chart. Now, how do we do this with the classical method? Okay, so we're drawing our thing here. It's going to look something like that, right? It's not symmetric. Okay, so I've got my alpha of 0.05, still got my 10 degrees of freedom. So if I'm looking at the, okay, so let's think about this for a second. Let's go back at the picture. This tells me what's to the right. Okay, I want what? So with my null hypothesis, my null hypothesis is sigma is less than 0.75, and my alternative hypothesis, no, it's equal to. My alternative is sigma is less than 0.75, right? So I want a left-tailed test, right? Problem is, this is giving me the right-tailed test. Okay? So, if I want 5% on the left, how much do I want on the right? I want 95% on the right. Okay? So, I'm looking at the 0.95 column.
So you do 1 minus your alpha.
1 minus your alpha in this case. Okay? Because I want it on the left. Okay? So when I'm looking at my 0.95 column, 10 degrees of freedom, that gives me that value there at 3.940. So at 3.940, that tells me, I didn't draw that very well. Put it over right there, okay? 3.940, that tells me that area there is my alpha equals 0.05. 5% to the left. 95% to the right. Okay, does that make sense? Okay, so now what value did I get? I got 7.29. Is that in my rejection region or is that in my do not rejection region? Do not reject. So that's over here, 7.29 somewhere. Okay, does that make sense? So still do not reject. Now I had somebody ask me, well, she said, well, why did you draw it over there? Why didn't you draw it over here? What value should be right here at the end? 0. And the chi-square is always positive. If you get a negative value, you did something wrong. Okay? So do not reject. So there's a bunch of different ways to do that.
Where did the 3.940?
3.940 came from the 95% column.
Okay.
Okay? You want 95% to the right, 5% to the left. Okay? Now, are you guys getting this? I had a student last class, he's been serving all semester, he's like, I'm getting this. It's like, good. So So this is the first time, I think I mentioned it before, first time I've given you guys the outline before the review. So I'm hoping that that really is helping. Do you think that's helping?
Yeah.
Okay.
So you get the steps down first.
All right. Have a great weekend. Quiz Monday is on 10.4.
Go down.
Go Utes.